Aloha. The replication crisis, also known as the replicability or reproducibility crisis, is a major methodological issue impacting various scientific fields, particularly medical and social sciences. This crisis refers to the widespread difficulty or inability to reproduce the results of numerous scientific studies, raising concerns about the reliability of findings and the validity of the theories built upon them. For instance, a 2011 study by Bayer researchers reported that out of 67 drug target validation studies, less than 25% could be replicated. Similarly, in 2012 researchers at Amgen attempted to replicate 53 landmark cancer studies, and found that only 6 of them could be successfully replicated, which indicates a replication rate of about 11%. A key methodological flaw contributing to this crisis is the tendency of researchers to use all observations in their data analysis, leading to overfitting. When models are overly tailored to a specific dataset, they may perform well retrospectively, but fail to generalize to new, unseen data. The solution might be readily available. If the research community had maintained an open mind to new ideas, many research findings could have been more effectively replicated. Back in 1948, A.K. Kurtz suggested using cross-validation method to verify the replicability of results, particularly for the Rorschach test. The Rorschach test is a projective psychological test involving the interpretation of ambiguous inkblots, but it has been widely criticized for its inconsistencies and unreliability as a diagnostic tool. The idea of simple cross-validation is very simple. Rather than using all observations in one single analysis, the researcher partitions the data into 2 subsets. The first subsample is used to propose a model, and then the second one is used to verify the model. In 1951, Mosier extended Kurtz's simple cross-validation by introducing double cross-validation. Kruse and Fuller further extended the concept of cross-validation by introducing multi-cross-validation in 1982. Multi-cross-validation involves repeating double cross-validation procedures multiple times by randomly selecting subsamples from the data set, which helps in improving the reliability of the validation process. In simple terms, instead of waiting for another researcher to replicate your study, you can perform replication yourself using the existing sample. This is do-it-yourself (DIY) in research. Cross-validation, Fisher's exact test, jackknife, and bootstrapping fall under a broader category known as resampling methods. As the name suggests, these methods involve reusing the existing sample in various ways to improve the reliability and replicability of results. Unfortunately, these methods were rarely used in the research community even though the replication crisis grew to an alarming rate. Cross-validation was not widely taught or discussed in mainstream statistical education and literature. As a result, it was largely overshadowed by classical statistical methods based on sampling distributions. Nonetheless, the rapid growth of computing capabilities, particularly since the 1980s and 1990s, made it feasible to implement cross-validation. In addition, the rise of machine learning emphasized predictive accuracy over analytical interpretability. It necessitates robust methods for model evaluation. Cross-validation provides a reliable way to estimate generalization performance. In modern data science workflows, it is almost essential to randomly partition the data into 2 or 3 subsets, commonly referred to as training, validation, and testing sets. You can take this a step further with techniques like K-fold cross-validation. K refers to the number of subsets or folds into which the data set is divided. However, for this discussion, we'll focus on the simpler approach of using 2 or 3 subsets. As their names suggest, the training set is used to train the algorithm and develop an initial model. The remaining subsets are then used to validate and test the model. Predictably, the model's performance on the training set often appears excellent. However, this is frequently due to overfitting, where the model is overly tailored to the training data and struggles to generalize to new datasets. When the model is applied to the validation or testing subsets, its performance may decline. While this drop in performance might seem disappointing, it is actually a blessing in disguise. These less optimistic results provide a more realistic indication of how well the model will perform in broader, real-world settings, helping you assess its generalizability and avoid overconfidence in the initial findings. When cross-validation is used, the data are randomly partitioned into subsets. Consequently, even if the same procedure is repeated, the data analyst can only obtain a similar, but not exactly the same result. The conclusion may remain identical, which is a good news for replication. However, the output number varies slightly. When I introduce cross-validation and other resampling techniques to my students and friends, the common response is often one of surprise. Why can't I see the same result every time? Some even describe it as unsettling, arguing that it seems to violate the principle of objective science. For me, however, this variability is not a flaw but a feature, one that reflects a deeper understanding of ultimate reality. The philosophy underlying classical statistics often assumes the existence of a single, true answer waiting to be uncovered. While this view offers simplicity and clarity, I find it overly deterministic and disconnected from the complexity of the world we observe. I align more closely with the worldview of quantum mechanics, which embraces uncertainty and acknowledges the existence of multiple valid outcomes for the same event. Far from undermining the principles of science, the non-deterministic, probabilistic view aligns with modern scientific paradigms. In quantum mechanics, for instance, the wave function does not describe a single deterministic outcome but rather the probabilities of various potential outcomes. Similarly, cross-validation reveals the range of possibilities inherent in our data and models, helping us appreciate the complexity and richness of the phenomena we seek to understand. From this perspective, the variability in results from different random partitions in cross-validation is not only expected but also normal and meaningful. It reflects the nuances of the data and the inherent uncertainty of real-world phenomena. Similarly, when we replicate a study by collecting a new dataset in a different context, we often observe variations in the results. This reinforces the idea that truth in empirical research is not absolute but probabilistic, shaped by the interplay of random influences and underlying patterns. I hope this information is helpful to you. Thank you for watching. Happy resampling!